Okay. Yeah, it's I'm very glad to hear that there is so much progress going on, and all of these should lead to successful demonstrations of error correction, right?
Well, indeed. I mean, and there's been a slew of error correction demonstrations, but in some sense, the really dramatic progress for me in error correction over the last 6 months now has been the surge of interest in new error correcting architectures. Quantum LDPC codes offering a much more efficient ratio of physical to logical qubits have been an aspiration of the theoretical community for some time. But we've now got no less than 3 groups this year have come up with much more specific proposals for what they're doing to develop quantum LDPC code enabled architectures. Photonic Inc., notably the first startup to commit to a QLDPC code architecture. Noticeably, IBM publishing a specific proposal for a quantum LDPC based memory system, and interestingly pointing out that the potential fit with its basic cubic layout architecture, so making it not sound easy, but making it sound like something that could very much be progressed in an engineering sense. And then QERA with their proposal for how we can use QLDPC codes to squeeze more out of the already enhanced module sizes we can expect from neutral atoms. The other line of interesting development in error correction we shouldn't forget, of course, is developments like Alice and Bob with their cat qubits, and they've got to the point now where they're working with multiple cat qubits. It'll be very interesting to see the performance stats coming out of those devices as they progress them. Very interesting to see architectures out there which are providing a new path to getting higher qubit fidelities, whether that's new microwave trapped ion gate approaches that promise to get to 4 nines fidelity and above, whether it's Microsoft, who have now been much more specific about their roadmap for their topological qubits, based on their non-abelian anions, and they're not saying that these topological qubits are going to be so high fidelity in their own, but they're going to be potentially a high enough fidelity that they get on to a much lower overhead in terms of the physical to logical qubits that they have to endure. So all this progress in a slightly wider sense of error correction, I think, is very interesting about how it potentially disrupts the assumptions that we've made in the sector for some time.
Thank you so much, David. That was a pleasure. This was the state of play quantum hardware update from GQA.
Super.